So we have one more week left, right? Next week is the last. Are you guys holding up well? Hopefully. We'll have an exam on the 20th, just to remind you. And basically we have only 3 lectures left. We'll cover interconnects for sure, and we'll see how far along we get. If we have time, we'll cover some other things as well. Okay. So let's start with interconnects. Now you know the assignment, so maybe we'll talk about the assignments in the break or tomorrow. Okay, I guess before I start interconnects, there's a multi-core and cache coherence lab 5, which is out. You probably know about that. It's optional. It's bonus. It's fun, I think. You essentially extend everything to multi-core. Cache coherence is the hardest part, I think. Multi-core is the easy part. Everybody can put multiple cores together, but keeping them coherent is the hard part. So it'll be a lot of fun, I think, if you want to do it. But you'll learn a lot, I think, about cache coherence. And this lab exercise is just part of the difficulties in building a cache coherent system in real life. So if you actually go and design multi-core processors in real life, you'll have to design a protocol like this. And protocol is usually much more complicated than what you're going to design. And even the protocol that you're designing, the MESI protocol, is not simple to get it working correctly in a real system because of the race conditions that you will see if you do the lab. Has everyone watched the lecture on multi-core? Okay. Okay, cool. Yeah, please do watch it before you attempt the lab. Please do watch it regardless. It's a good lecture. Unfortunately, I had to be at a conference and places last week. That's why you had the online lecture. Do you guys like those online lectures? Not as much? Who likes them more than being here? Because it's a preference in general. Who likes being here more than the online? Okay. Well, that's why you guys are here. I see. Maybe the ones who are not here, we should ask them also. I find it's very personal, but it's good that you guys are here. Okay, so we'll continue with interconnects. And interconnects are really critical for scalability of the system. And this is a really fun topic, I think. We could actually have a course on interconnects. We could actually have a course on many of the topics that we've discussed. But interconnects are especially bigger. So this is a summary of last week. Juan talked about GPU programming, and then in the online lecture we have the multiprocessor basics, memory ordering, and cache coherence. And some of the online lecture we already covered, like you should really know Amdahl's law very well. You should know bottlenecks in the parallel portion, which we covered before. So you probably remember the 3 fundamental bottlenecks in the parallel portion: synchronization, resource contention, and load imbalance, right? Those are 3 fundamental bottlenecks that essentially cause parallel part of a parallel program to be not completely parallel. And these are not accounted for in Amdahl's law, if you remember. Okay, so, with cache coherence, in the end, we were talking about systems that essentially are scalable or not scalable. And if you remember, if you watch the online lecture, you will see that I mentioned that scalability is very much determined by the interconnect as well as the protocol. So that's why interconnects fit in really well at this point. But interconnects are much more general, of course. So basically, we're going to talk about interconnection networks. Usually these are called networks also because they look like networks in the end. These are some required readings, well recommended and required, and we're going to cover some of them. So let's start with the basics first. I mean, these things exist everywhere. Internet is an interconnection network also, but interconnection networks are much, much more general than internet. They're on your chip. They're everywhere. Basically, the goal is to connect components. That's the purpose. And components may be many things. They could be processors and memories, processors and caches, I/O devices, basically all kinds of heterogeneous agents, things that compute, things that store data. And you can view this as something that looks like this. And this is just part of the interconnection network of a multiprocessor, as you can see over here. You have a multiprocessor system. And actually, in fact, you have disks over here also, and then they're connected through some interconnection network. It's just one example. But any component requires some kind of interconnection if you want to communicate. So why is it important? Clearly, it affects the scalability of the system. If you remember the coherence lecture, coherence is very much affected by your interconnect. For example, if you want to do Snoopy bus coherence, Snoopy coherence, having a bus is nice because whenever you actually do a read or write, you broadcast it on the bus, and everybody sees the bus. Right? How do you do Snoopy coherence on a much more scalable system? Because bus doesn't scale, as we will see, as we also briefly discussed in the coherence lecture. That's very much dependent on your interconnect and the protocol you build on top of it. Basically, interconnects affect how large of a system can you build and how easily can you add more processors, for example. Internet is, for example, a very scalable system that has some sort of interconnect, but it's very loose if you think about it. This also affects performance and energy efficiency. How fast can processors, caches, and memory communicate? Do coherence, for example. How long are the latencies to memory? How much energy is spent on communication? And we've already seen some of this, right? If you remember the latency in DRAM, we talked about how interconnect affects that latency. We talked about the idea of tiered latency DRAM, which is essentially chopping the interconnect into two pieces, segmenting the bit lines such that there is a portion that's smaller, shorter, closer to the sensing structures, and that's faster as a result. And there's a portion that's longer and farther away from the sensing structures. As a result, it's slower. So that's an example of a simple interconnect, essentially a bus or a wire, chopped into two pieces, segmented using an isolation transistor. And it's clear, if you remember, it does affect all of these. It affects performance, it affects energy efficiency, and it does affect also scalability. In that case, the scalability was really the capacity of the DRAM chip, right? How big of a DRAM chip that you can get given an area constraint. Okay, so I'll give you some terminology to begin with. There's a lot of terminology in this area, actually. I'll try to minimize it, but you cannot avoid some terminology. We're going to talk about three major things in interconnection networks. And these three things are interrelated to each other: topology, routing, and buffering and flow control. So what are these? Topology essentially specifies the way switches are wired. You have switches. Switches are the things that route packets, route things that need to be communicated. And topology specifies that. It affects everything, basically. It affects how you do the routing, your reliability, your throughput, latency, how easily you can build it. And we will, that's why we'll start with the topology. The topology can be a bus, for example, as we've seen before, right? Or it could be a two-dimensional mesh. It could be a torus. It could be a butterfly network. And we're going to get even more fancy after that. Or it could be unstructured. Like internet topology is very unstructured, right? You could wire things in very different ways, and it's completely dynamic. Whereas if you're building a multiprocessor, you can be very structured. You could just have a bus connecting things, or you could have rings, as we will see. So a routing algorithm basically determines how does a message get from a source to a destination. There are many versions of this, and we will talk about that. It could be static, it could be adaptive, and there could be multiple ways of doing it. We'll talk about that. And buffering and flow control basically determine what do we store within the network, within a router. Do we store the entire packet? Do we store part of the packets? Do we store nothing in the router? We'll see examples of this. And also, how do we throttle during oversubscription? If you have congestion in the network, how do you handle that? How do you ensure, for example, if you have buffers in a router, how do you ensure that those buffers don't overflow? That's called flow control. Essentially, you control the flow of messages in the network such that you don't run into situations where you cannot handle the messages. Or you don't run into situations where your performance degrades significantly because you have too many messages in the system. If you remember one of the lectures, I don't remember which lecture, but we talked actually in the memory interference and quality of service lecture, we draw the load latency curve, right? On the x-axis, we had the load. On the y-axis, we had the latency. And the curve looked like this. And if I can find my, I don't know where these are. OK, there. That's better. Now, does this thing work? Oh. OK. Yeah, I'll just bring it up again because we're going to get back to this load latency curve again. So if you remember this is your load. How much load do you put on the system? And this is the latency. And the curve looks like this. And essentially, your topology affects this. With topology 1, You can have a curve like this. With topology 2, you can have a curve like this. Actually, all of these three things affect your load latency curve. But flow control is one example of the things that affect the load latency curve, and we're going to talk about that. But keep this in mind. Okay. So buffering and flow control are tightly coupled with the routing strategy also. Of course, your topology determines how you can route things because it determines how things are connected to each other, right? And you want to get from one source to another destination. Okay, more terminology. We're going to have a lot more going forward. But some of these are easy. Network interface is a module that connects endpoints or processors to the network. It essentially decouples communication and computation. It's another way of thinking about it. You have a network interface, and once you go through the network interface, you're communicating, not computing anymore. Although going forward, it may not be the best way of thinking about things. Link is a bundle of wires that carry a signal. Hopefully this is obvious. Switch and router connects a fixed number of input channels to a fixed number of output channels. Essentially, switch and router is the thing that routes the messages from one place to another place. And you may have many, many switches. Hopefully these are simple. Has anybody taken a networking course? Okay, that's good. So you've seen this terminology in some form at least, although sometimes the terminology differs. Okay, and channel is a single logical connection between routers and switches. So you can have channel between one router and another router. So we'll see some of these, and the papers that you are reading cover some of this also. So more terminology, node, hopefully it's obvious, it's a router or switch within a network. A node doesn't need to have a processor, but it can also have a compute unit. It's very general. It can just be a router, yeah. Message is the unit of transfer for network's clients, basically processors and memory. Essentially, this is the thing that you want to communicate at the higher level. A processor wants to send a message to memory, for example, and the message may be, I want to write to this location. And that message is broken down into packets. Packets are essentially unit of transfer for the network. And that packet can be broken down into flits. Flit is also called flow control digit. It's a made-up term. Everything is made up, actually. But basically, it's the unit of flow control within the network. So you don't have to do the flow control or routing at the packet level. You can do it at the flit level, at a much smaller granularity, basically. So essentially, you can think of messages as what you want to communicate. You break it down into smaller packets. And packets may be the granularity of routing, for example. You determine the routing for a packet. And then you break it down into individual flits. And flits may be the granularity of flow control, meaning you don't send the entire packet from this router to this other router, but you send flit by flit, right? And that way you can actually keep your links smaller. For example, your packet may be 64 bytes, but your flit may be 8 bytes, right? That way you can have 8-byte links, and you can send the 64-byte packet in 8 cycles. It doesn't have to be consecutive cycles, because you can interleave those cycles with other flits on the same link. Okay, so that's just some terminology so that you can keep this in mind. And again, you can do the routing at the flit level also, as we will see later on. You don't have to do the routing at the packet level, but you can still have packets. Okay, some more terminology. Direct or indirect networks. You may not have seen this before. Basically, in direct networks, the endpoints, the receivers sit inside the network. In indirect networks, they sit outside the network. So this is an example of an indirect network. Basically, you want to communicate between, let's say, these endpoints and these endpoints. You can think of this, let's say, as processors communicating with some memory banks. And endpoints, that the things that are communicating sit outside the network. And the network consists of essentially these switches. These are the switches that you have over here. And they basically are there just to route messages. They're not endpoints, meaning that they're not the receivers of any message. They're basically the transmitters. They just convey the message. And this is an example of a butterfly network, by the way. This basically is one topology that's connected as a butterfly network. We will see that in a little bit. So the sole purpose of the network over here is to route messages. Endpoints do not sit within the network. There's some more terminology over here. As you can see, this router over here, or switch, has a radix of 2. which means that it has 2 inputs and 2 outputs. And usually this is abbreviated as radix array or 2-array. These routers are essentially 2-array. If you see that term in some interconnection network literature, that's what it means basically. That's the radix of the router. And in this case, you have 2 inputs and 2 outputs, but you can have a router that has 5 inputs and 5 outputs also, as we will see in a mesh network. But this is not a mesh network, as you can see. It's a butterfly network. Its routers are simple, but its connectivity is not as much as mesh, as you can see. So this is indirect, and this is the mesh. This is, in this case, I made a direct mesh because the green parts are essentially everywhere, as you can see. It's inside the network also. It's a direct network. Every node is both an endpoint and a switch in this case. And you can see the routers over here, at least this router over here is 4-array. Actually, it's 5-array because there's an input port and an output port into the green thing over here also. And then there are 4 input ports and 4 output ports to the neighbors. And you can see that not all routers are equal in a mesh. The router over here has only 2 neighbors and one endpoint connected to it. Okay? So now you know the difference between direct and indirect networks. And we'll see the trade-offs between the topologies soon. Okay, so let's go into topology. That's one of the most important things that determines performance and everything else in a network. I'll give you a little bit more terminology. So topology has also terminology, but hopefully these will become clear. And you don't need all of this actually in what is going to follow. So topology can be regular or irregular. Essentially, it could be, as we saw, a mesh is very regular. It's a regular graph. A ring is very regular. Whereas if you look at internet, it's very irregular, right? There's no topology that you can actually constrain in the internet. Whereas in mesh, we know that it's constrained by this two dimensions. Routing distance is the number of links or hops along a route. If you want to go from one node to another node, how many hops do you need to traverse to get from that source to destination? That's the routing distance. And of course, this is dependent on the route. Usually you have a maximum routing distance that has a special name. It's called diameter. It's essentially the maximum distance between any source and any destination in the network. It's called the diameter of the network. That's used as determining the quality of a network, quality of a topology, right? If your diameter is too long, that means that you may have cases where you have to go through that route. As a result, your worst case latency is determined by your diameter. So in general, it's good to have lower diameter topologies to minimize the latency, if possible. Of course, as you scale up, it's hard to keep the diameter low because if you have a billion nodes, let's say, I'm just making it up, how do you actually ensure that every node is connected to every other within one hop? Diameter 1 requires you have only one hop between them, right? Not so easy. Average distance is the average number of hops across all valid routes. Of course, this may be a better metric, but you don't know exactly. Then the question is, how do you compute the average, right? It's dependent on a workload, usually, or you could assume some patterns, traffic patterns. You could assume all nodes communicate with, all sources communicate with all destinations with equal probability and randomly. That's called uniform random traffic. And you could compute an average distance based on that analytically. You don't need a workload for that, right? You're assuming a workload. Or you could assume some other sort of traffic pattern, which we will see later on, and you could compute an average distance based on that. So these are some metrics that are associated with a topology. But they also determine the performance of the network in the end. Is this clear? Hopefully it's relatively simple. And we will see some examples of this in a little bit. There's another metric that you will see. It's called bisection bandwidth. I don't like it that much for the reasons that I'm going to tell you. This is often used to describe network performance, but this is old times. New times, we're more application oriented. Essentially, you can compute what's called the bisection bandwidth of a network by cutting the network in half and summing the bandwidth of the links that you actually cut or sever. You can think of that as a minimum number of channels spanning the two halves of the network times the bandwidth of each channel. This essentially is meaningful only for topologies that are recursive or that are symmetric across the thing that is cut. It can be misleading because it doesn't account for switch and routing efficiency, and it basically assumes some traffic pattern, right? If you're not communicating between those links, then maybe it's not that interesting. But I'm giving this to you because you may actually see bisection bandwidth as a network performance metric used in some papers. But I would suggest not being fooled by this particular metric that much. In the end, what matters is your overall performance, right? And execution time. There's also another distinction between blocking and non-blocking network. I don't want to dump too much terminology on you. This is not also as important. But basically, if connecting any permutation of source and destination is possible, the network is non-blocking. Otherwise, the network is blocking. So basically, is it possible to connect any permutation of sources and destinations? And you can also have rearrangeable non-blocking. It's the same as non-blocking, but you might require rearranging connections when switching from one permutation to another. It's not that important. Well, I'm not going to test you on non-blocking and blocking. Diameter is important. Diameter basically determines your worst case latency, right? Okay, so we're going to cover some topologies. We're going to start with the simplest one, and then we're going to jump back and forth between complex and simple ones. Bus is the simplest one. Point-to-point connection is the ideal, but the most costly one. It's the exact opposite of a bus, essentially. And then we're going to try to reduce the cost of the point-to-point. And then we're going to make it a little bit more complicated. So let's see. There are a bunch of topologies that are proposed. It's impossible to cover all possible topologies that are out there. Some of them are more complicated than others. But they have all different properties. And they all affect your performance. So let's talk about some metrics to evaluate interconnection network topology. We're going to focus on topology first. So cost is important. So cost is affected by how many switches you have, how many wires you have, for example. Latency in hops or in nanoseconds. These are not necessarily the same thing. You may actually have hops. You may actually have many hops, but your interconnect may be low latency potential and your routing efficiency may be high. But usually having fewer hops, a smaller diameter is good because you don't need to go through many routers. And whenever you need to go through a router, there's some overhead associated with going through the router. Now you're basically dependent on how fast you can switch, you can route through that router. If you don't have a router, if you just have interconnect, your latency is dominated by the interconnect, right? Essentially, how fast you can move an electron from this place to this other place, assuming you're moving electrons. So contention is also important, how much contention happens because of the way switches are wired together, essentially the topology. And topology is very much affects contention. There are also many others that exist that you should think about, like energy, bandwidth, overall system performance. Of course, now this becomes more fuzzy in the sense that it becomes a lot more workload dependent as we go from, these metrics are easier to determine without thinking too much about workloads, but these metrics are harder to determine without thinking about workloads. So we're going to use these, but always think about the other metrics that we will get into. So this is the simplest topology. We've seen this before, right? When we talked about the cache coherent Snoopy bus. Essentially, this is a bus. And again, this doesn't need to be processors over here. This could be any sort of endpoints that are communicating with each other. But think about these as processors for now. You have 8 processors over here that are connected to a single wire in the simplest case. All nodes connected to a single link, essentially. And this is another example of it over here. This is a Snoopy cache example. Caches are connected to this bus, and they can observe their actions. So clearly, this is very simple. And it's very cost effective for a small number of nodes because you could keep the interconnect over there and connect new things on top of it. And a big advantage of this is it's easy to implement coherence on this because everybody sees everybody's actions. Whenever this processor 0 wants to communicate with processor 1, it sends a message, and that message gets broadcast on the bus, right? So you can actually do easy snooping. You can serialize a request easily. So it's nice. But the downside is scalability, as we've also briefly discussed. Essentially, if you want to increase the number of nodes that are connected to this bus, you have multiple issues. What are those multiple issues? First of all, you'll run into electrical loading issues because this is a single bus. And if you have a lot of drop points on top of that bus, you probably cannot run that bus at very high frequency. As a result, your frequency reduces your bandwidth reduces because of that. Now, to solve this problem, people have looked at segmenting the bus, meaning having segments over here, but that now it complicates the bus a little bit more and gets rid of some of the properties, like what we've discussed over here, right? Easier to implement snooping. And also, scalability is limited because of electrical loading. That's one reason. But the other reason is you have high contention, meaning if this processor wants to communicate with this processor, it uses the bus. And while it's using the bus, this processor cannot communicate with this processor because the bus is busy, right? Meaning that because you have a single link, you cannot communicate between processors that are disjoint from each other. And that's fundamentally the limitation of the bus. You get into high contention, basically your bus saturates fast, especially if you have a lot of communication requirements between the processors, because you only have a single link. Makes sense, right? So there are two reasons you get scalability issues. One is electrical loading, and the second is because of high contention. Okay, so let's look at the opposite end. So I'm going to start with two opposite ends. Bus is the simplest one. Point-to-point is the most extreme one. Basically, in point-to-point networks, every node is connected to every other directly, with direct links and isolated links. So if the node 0 wants to communicate with node 1, it can go through its own link. And if it also wants to communicate with node 7, it can go through its own link. And other nodes can communicate with each other also. Basically, it looks like this. As you can see, it's pretty expensive. But this leads to the lowest contention because there is no contention actually between pairs of communicating nodes. Node 0 can communicate with node 7, and node 3 can communicate with node 4. And essentially, there is no contention. No contention means there is no information also, because you don't know who is communicating with whom if you're sitting somewhere outside. Which means that if you want to build a Snoopy bus on top of that, a Snoopy cache coherence protocol on top of this, good luck. Because Snoopy cache coherence assumes that you see other processors' actions, right? In this case, you don't see. So that's one of the downsides. But it gives you lowest contention, right? If you're doing a lot of communication, this is great. Potentially, this is lowest latency because it's its diameter is 1, right? This is a diameter 1 network. There's only one hop between any source and any destination. And it's constant latency. So it's ideal, clearly, in terms of latency and in terms of diameter. So this could be great. And there's no switching overhead except when you decide where to communicate. So you need to have switching overhead to decide where to send the message, right? In the source node. That's it. And maybe in the destination node, depending on how you receive the messages. But there's no switching overhead inside the network. So you're very much bound by the interconnect latency. And as a result, it's ideal. But in terms of cost, it's not necessarily ideal, clearly. Right? This looks very costly, even when you look at it. And if you want to draw this for 1 million nodes, that'll be fun, probably. It'll look nice, but you may not be able to see much after that. OK, so clearly, as I said, it's highest cost, because now you have an order of n connections and ports per node, an order of n square links. And that's the big downside. That's why these are not built except for very simple systems. And because of that, it's not scalable. Right? Its scalability is, if you look at bus, it's too simple. As a result, it's not scalable. And it's on this end of the spectrum. If you look at point-to-point, it's too complex. As a result, it's not scalable. That's why people have developed a lot of topologies in between. And also, there's this issue. How do you lay this out on a chip? So if you're doing this on a chip, there are a lot of wires that are crossing each other, right? You need to basically have a lot of metal layers to lay this out. 8 may not be that bad, but if you scale this up to 16, 32, 64, 1,000, now it becomes basically insurmountable. It's very difficult to lay this out. So we're going to talk about laying it out on a chip. And if you think about this as a network, not necessarily on a chip, same issue exists basically, right? You need to basically route the wires physically from one node to another. And even if you have 8 processors, essentially you need to connect them somehow, and it becomes not so easy to do that wiring. Whereas if you have a bus, basically you just connect a single wire to 4 different processors. That's it. But this one's very hard. So if you have 1 million nodes in a supercomputer, and if you want to do point-to-point connections, the engineer who's really doing the wiring over there probably goes crazy. And this is something to also consider, because there are other topologies that are not as bad, but they're also difficult to wire. And you can think about, so I'm not talking about technology right now, right? These are actually technology agnostic. So you can have optical technology. There are similar issues. Okay, okay, so now the question is, we have the 2 endpoints, extremely simple, extremely complex, none of which are scalable. So how do we achieve scalability at reasonable cost and reasonable latency? Now we're going to explore the space that's in between the bus and the point-to-point. I'm going to start with point-to-point and make it a little bit simpler. And that's the idea of a crossbar. In Crossbar, every node is connected to every other with a shared link for each destination. So it's a bit simpler than point-to-point. You don't have point-to-point. You have a shared link. Let's assume that these are the destinations. You have a shared link for each destination, and you basically have cross points, if you will, coming from each source. So if you want to transfer from 7 to 0, you go through this link. If you want to transfer from 6 to 7, 6 to 6, let's say, or 6 to 5, you go through this link, and they do not contend with each other. But if both of them want to transfer to 0, 7 transfer to 0, and 6 transfer to 0, they share the link. So cost is reduced because of that shared link. Contention is increased, but it's more scalable. It's easier to deal with. So it basically enables concurrent transfers to non-conflicting destinations, as I mentioned. If the destinations are non-conflicting, there is no shared link. So the same source or different sources can transfer to different destinations concurrently, which is good, which is not possible in a bus, clearly. But you have some contention, of course, when your destination is shared. And you need to have some sort of routing, some sort of contention resolution. But this could be cost effective for a small number of nodes, and it's actually used, as we will see. So what are the properties of this? This is low latency and high throughput. You can see very high concurrency over here. But the downside, there is still downsides. It's expensive. It's not scalable because you have ON square cost. It's a little bit different from this ON square that we saw over here. This is really ON square, but this is still ON square. So the number of components that you have still grows N square, but it's connected in a different way, as you can see over here, right? It's not direct links, but you're basically sharing the destination link over here between the sources. And there's also another issue. It's difficult to arbitrate as N increases, because you have a shared link, and your N increases over here. So how do you arbitrate for that shared link? Actually, arbitration complexity, in this case, I look at it over here. Your arbitration complexity increases over here. You can think of this mux becoming much bigger if you want to arbitrate for a shared destination. If everybody wants to transfer to destination 0 over here, you need to do that arbitration, and you need to do that efficiently. So it's not as easy to build as you increase the number of, as you increase N, basically. But if your N is small, this is actually not bad, because it gets you a lot of the benefit of point-to-point connections without a lot of the cost of it. And this is used in core-to-cache bank networks in many systems. These are some of the early systems that use them. I'm going to give you examples. But we'll take a look at that in a little bit more detail. So this is another crossbar design. This is actually interesting. Basically, this shows kind of the arbiters over here. Basically, if you're transferring from 0 to here, you need to actually ensure that basically you need to arbitrate across the shared link somehow and decide which one is loading its data onto the shared red link. And you could build in the different ways. You could have a version that actually has buffers over here that basically buffers the data that's supposed to be sent from 0 to, let's say, 0 over here. You could have a version that doesn't have buffers. And now you run into other trade-offs, right? If, for example, you have buffers, yeah, maybe you put the arbitration complexity over here. If you don't have buffers, then you need to somehow sense if somebody else is going to send something to this link. So there are different ways of building this arbiter There are bufferless arbiters, there are buffered arbiters. We're going to look at that later on again. But keep this in mind for now. How do you do this arbitration is not so easy. Okay, so let's look at a real version of this. So this is one of the earliest multi-core crossbars. It was in Sun Ultra Spark T2. If you remember Sun Niagara, this is Niagara number 2. This is one of the simplest processors in terms of processor complexity in order, if you remember. So if you look at the core to cache bank networks, it's essentially a crossbar over here. And you have these cores that are sending requests to the buffers. And each core has its own buffers, as you can see. It's 2 entry buffers, I think. Yeah, 2 deep queue for each source destination pair. And then you have an arbiter that looks like this. Essentially, it's a MUX, right? So these are the these are the requests that are going to bank 0 from all the cores. And each core can have at most 2 requests, or 2 flits, let's say in this case. And basically, the arbiter decides which one to take, such that the bank 0 can serve that through this tree of MUXes. Right? That's one way of building the arbiter, and that's a real design. So this thing needs to be built, and it's not easy. And this is the other side. So basically, you have this arbiter for every bank, and also the non-cacheable unit. And you have also the other way, which is banks need to communicate back to the cores. So you have the arbitration on the other way as well, going to different cores. For each core, you have a different arbiter. And as you can see, you have 8 cores, 8 L2 banks, and 1 non-cacheable unit. So it's an 8 to 9 crossbar, I think. And you have a 4-stage pipeline in the arbiter. You send the request, you do the arbitration, you do the selection, and then the transmission. So it takes 4 cycles, at least, to get there, to the destination. And as you can see over here, you have a 2 deep queue for each source destination pair. So this is built, it's real. But if you imagine building this for 1,000 to 1,000 crossbar, it's not easy. Because now your arbiter becomes much harder, right? And there's no easy way around it, right? So what is the bufferless arbiter? So if you want to build a bufferless arbiter, then you need to essentially get rid of these things over here, the buffers. And you need to somehow sense whether any core is sending a message to any bank. And based on that sensing, you basically need to say, okay, this core is granted and every other one is not granted. So you could actually get rid of the buffers. It's not as easy to build. Also, buffers give you better timing, because once you buffer something, you actually have more time to do the arbitration. But if you don't buffer, then you need to actually do some sort of arbitration somehow. Okay. So, okay, I guess I already talked about bufferless and buffered. So this is the bufferless crossbar. You don't see buffers over here. And basically, you need to do some sort of sensing to figure out who is allowed to use the red link, who's allowed to use the yellow link, who's allowed to use the green link, and who's allowed to use the blue link. If you have buffers, the trade-off is that you can send the message without thinking about whether or not you're allowed to use it. Things get buffered over here, and you still have an output arbiter over here, which is very similar to what is right here. This is essentially an output arbiter. Each bank has an arbiter. Basically, each bank over here has an arbiter. And it looks at the buffers. And the timing is easier, but you have additional complexity. You certainly have the buffers, and you need to have flow control. Now, what does that mean? Well, these are limited resources, right? So you cannot keep sending essentially messages into these buffers. You need to know whether you're allowed to send it, whether the buffer is full or not, or is going to get full or not. So there needs to be some mechanism, back pressure mechanism, saying, oh, you cannot send messages to this buffer anymore. So now we've added a lot more complexity. So the trade-off is no buffers, no flow control, or some other sort of flow control. Flow control is really in the arbitration mechanism over here, right? But the arbitration mechanism may not be as easy over here. Here, arbitration mechanism a little bit more relaxed, because you have buffers and you've latched everything, and then you have the full cycle to do the arbitration. But now you have buffers, a lot of buffers perhaps, and also you need to have flow control to manage the buffers. So this is the buffer management overhead, and that adds more cycles, as we will see. Okay, so even the crossbar, something as simple as crossbar, requires thought to build. and also a lot of engineering. And you can think of Crossbar as very simple, I think. Yes?
You also like implement fairness?
Yeah, exactly. So there are other, we haven't even talked about fairness over here, right? How do you put fairness into the output arbitrary? And you usually want to implement some sort of fairness. And this goes back to a lot of the algorithms that we discussed earlier. So you could do round robin, for example, but that's not fair, as we've discussed in the past. So all sorts of issues like fairness exist over here also. Very good point. Okay, so if you have buffered crossbar, it's simpler arbitration and scheduling, as we've discussed. You also have efficient support for variable size packets. Actually, bufferless is a little bit harder, but it's doable. But it's easier with buffered, because with buffers, you can say, I'm going to buffer 8-byte stuff, right? 8-byte flits, let's say. And you could basically break anything into 8-byte things, right? But this requires n-square buffers, in this case, or n-square, I should say, depending on how many things you want to buffer over here. And also, it requires flow control, which is not set over here, which should be. Okay, so we're going to get back to this bufferless buffered thing, and maybe we're going to get back to fairness and quality of service also. So now we have the crossbar. It's good for small-scale networks, but it's still not scalable. Can we get lower cost than a crossbar, yet still have low contention compared to a bus? We don't want to go through the bus, but we don't want to build the crossbar for a 1,000 by 1,000 network, but we want to be somewhere in the middle. And the idea has been developed that's called multistage networks. It's a really old idea. I'm going to cite a paper from 1970s on this. Essentially, they're also called multistage logarithmic network because they look logarithmic. As we will see, usually their cost and latency scale with log n. These are essentially indirect networks with multiple layers of switches between terminals and nodes. Indirect because endpoints sit outside the network. Inside, you just have routers or switches. So if you look over here, this is one example of this. This is an omega network. Basically, the network type is determined by how switches are wired internally. And you don't need to remember what an omega network looks like. But it looks like this, basically, at least in the 8x8 version. But if you look at the cost of this, it's n log n over here. And latency is log n. Basically, you have 3 stages because you have 8 nodes over here. And the cost is basically log n stages times n switches or endpoints in each. That's the idea. Simple, right? And we're going to see some examples of this. So let's take a look at the example communication. Let's assume that you want to communicate from this core to this cache bank. I'm going to use that example. Core 7 wants to communicate with cache bank 7. Essentially, you go through, there's only one path you can communicate, right? Which is similar to a crossbar, actually. But the difference between this and the crossbar is you get contention in this case. This case, you have non-conflicting destinations. Destinations are different. Destination 6, bank 6, and bank 7. And you have non-conflicting sources. You should not get a conflict in a crossbar, but you do get a conflict over here because you have a shared resource, and that shared resource happens to be this stage in the multi-stage network, this switch, basically. And if these 2 packets happen to arrive at the same time on this switch, then they have to be serialized. They cannot be serviced at the same time. That's the idea. So we reduced the cost clearly from O(n) squared to log n, n log n, sorry. But it came at the cost of contention. Then the question is, how often does this happen? If it doesn't happen a lot, then that's good, right? Because if this node is communicating with this node, then there's no contention between this communication pattern. Okay, so that's the idea. So is this blocking or non-blocking? I'll leave that exercise to you. Okay, so multi-stage networks, there are many, many examples of this, and they could be built in different ways. I'll introduce the concept of circuit switching versus packet switching in this case. Basically, this is one example where you're circuit switched. Circuit switching means, actually, maybe I have a better example. No, I don't have a better example. Circuit switching means that whenever you're communicating between a source and a destination, you first set up the path. Setting up the path means you configure the switch router such that it transmits from that source to that destination. So for example, if you want to communicate from, let's say, node 0 to node 7, what do you need to do to set up a path? Basically, you need to somehow send a message saying that I want to set up communication between 0 and 7, and that message goes through, and basically there's some mechanism to figure out how to route from 0 to 7. If you want to route from 0 to 7, this switch needs to connect this input to this output, right? And then this switch needs to connect this input to this output, and this switch needs to connect this input to this output. So you basically statically set up those switches such that they are wired, statically meaning after, when you set up, they're wired to pass through this input to this output to this output, and this input to this output. And once you set that path up, you can send a message on that path, and it basically flows through the network, right? Because switches are set up that way. You don't change which input is connected to which output. That's the idea of circuit switching. You set up the path, and once the path is set up, communication is easy because essentially the data flows through the network. And it's constant latency. The latency is determined by how fast the data actually goes from here to here, which is good. And you can basically keep pushing packets from node 0 to node 7. That's great. And I think that's one advantage of multi-stage networks, because you can do this sort of circuit switching, set up the path, and you can have constant latency. Right? Every time you have constant latency, everything is 3 hops over here, right? Okay, and then the switch itself is a 2x2 crossbar that you need to set up. Okay, is there anything that so of course, once you set that up, set that path up, you cannot use these switches for any other communication path. That's the downside of circuit switching, because you already set the path up such that this input is connected to this input. So if this node wants to communicate with anything else, it cannot until that path is broken down and a new path is set up. So circuit switching is very efficient because you don't need to dynamically switch, as we will see in a little bit, and you're communicating between on the same path very quickly, but you're isolating that path, you're dedicating that path to that communication pattern, and if anything else needs to use that path, it cannot. Actually, any router that needs to be used by any other communication pattern cannot be used. You have to essentially tear down that circuit and then set up the circuit again. Does that make sense? Okay. But of course, there could be non-conflicting pairs of communicating sources and destinations. For example, you could do 0 to 7 communication, and at the same time, you could do 2 to 1, and they're not conflicting. So if you have a lot of non-conflicting paths, that's great. Okay, so let's see. Clearly, a multi-stage network, I think this is not dependent on circuit switching, but a multi-stage network has more restrictions on feasible concurrent transaction and receiver pairs as opposed to a crossbar. We've discussed that. And it's more scalable than crossbar in cost. Basically, it's O n log n for a butterfly network. This is a butterfly network. It's just the way switches are wired. Okay, so this is a packet switch version of it. Actually, if you have circuit switching, if you look over here, you don't need to have buffers, right? You just need to have a mechanism to set up the path. And after that, you don't need to buffer anything. So you get rid of the buffers. If you have packet switched, this is a buffered packet switch version. You could actually have a non-buffered packet switch version of this also. But let's assume buffers in this case. Basically, packet switch means you dynamically switch which input port is connected to which output port in each switch. In this cycle, you may connect this input port to this output port such that 0 can communicate downstream this way. In the next cycle, the router essentially switches such that this input is connected to this output port. So every cycle, you can have a different input connected to a different output port. That's called packet switching. You're really dynamically switching which input is connected to which output. It's much more flexible, clearly, Because now, when 0 is communicating with 7, 1 can do communication. They can interleave their communication across different cycles through the same router. Whereas previously it was not possible, because once you set up the path, 1 cannot use that path until you tear down and reset up the path for 1. So this is much more flexible, but now the router is more complicated, right? The router needs to be able to dynamically switch every cycle. And also there's an efficiency problem, which is every cycle you need to make a switching decision. You need to decide which input port is connected to which output port. And that takes time, and that takes energy. So that's the fundamental trade-off between packet switching and circuit switching. In the next slide, we're going to go into a little bit more detail. Okay. So essentially, circuit switching sets up full path before transmission, establishes route, and then sends data. It's much more general. And no one else can use those links while circuit is set. Packet switching routes packet in each router. It routes each packet individually, possibly via different paths. Although in this case, in this multi-stage network, you don't have many paths, right? If you want to communicate from 0 to 7, you have only one choice. You have to go through these routers. So this sort of multi-stage network doesn't have what is called path diversity. Path diversity is how many paths can you take to go from the same source to the same source destination pair. How many paths are connecting those? So if you have path diversity, you can take different paths potentially, and that's good for handling congestion, right? If you have contention in one particular path, you can choose the other path. That's good. In this case, you don't have path diversity because your cost is relatively small. As a result, you cannot route around congestion easily. Well, you cannot route around congestion actually. You have to block. But because you don't have path diversity, your routing is also simple. Okay. So I gave you another aside over here. So packet switching is more general because if link is free, any packet can now use it. So upside of circuit switching, you get faster arbitration. Once you set up the circuit, you know the input port is connected to the output port. You don't need to route after that point. Right? It's all connected, and basically the packet flows. There's no need for buffering. You fundamentally eliminate buffering in this case. But of course, the downside is setting up and breaking down the path takes time. And you need to have a mechanism for it. So some circuit switch networks actually use a separate network to enable this circuit. But that may not be great. And also, once you set up the circuit, no one else can use it actually can be problematic because if somebody else wants to use it, then you have to set up and bring down the path. Packet switching is potentially slower because you must dynamically switch. You need buffering, but you don't necessarily need that buffering. But there's no setup and bring down time. That's the upside over here. And it's much more conflict-free. It's more flexible. It doesn't underutilize links. You could underutilize links over here if multiple paths need to use the same switch. Okay. So I've given you multiple things over here. Circuit and packet switching choice is actually independent of the topology, right? Any topology can, this is really a higher level protocol decision on how a message gets sent to a destination. I just want to discuss it over here because it's a nice place to discuss it in multi-stage networks. Some topologies are more amenable to circuit versus packet switching. So that's why I wanted to discuss it over here. So let's go back to this multi-stage network. This is actually very nicely amenable to circuit switching, right? As I said, once you set up the circuit, you know exactly how long it'll take to the destination because this is there's no path diversity in this particular network, and every source is connected to every destination with O log n distance. So it's very nice in that sense. Whereas some other topologies are not very amenable to circuit switching, and setting up the circuit takes time. As we will see later on, for example, hypercube may not be very amenable. Mesh, okay, you could set up circuits, but in a mesh we will see that things may actually interfere with each other a lot also. Okay, so let's take a look at another example. This is another example over here, Delta Network. This is actually a very nice paper. I didn't assign it, but it's a relatively old paper that introduced this particular network. As you can see, it's a NISCA 1979. I'm not going to go through the analysis of these networks, but if you look at these papers, they analyze the cost and latency and ... It has a single path from source to destination, very similarly to what we've examined. Each stage, in this case, each stage has different routers. That's not true for the butterfly that we've seen. If you look at the butterfly, each stage has the same router. So in that sense, butterfly is nicer, because you can actually have the same router and replicate it. Whereas each stage in this case is not, it's not easy to route over here. And it was one of the earlier networks that were proposed to replace costly crossbars as processor memory interconnect. You had the processors over here, you have the memories, and you don't want crossbars, so multi-stage networks are a good idea. This is another example, Omega network. Actually, you've seen this before. You have a single path from source to destination. In this case, all stages are actually the same. You could actually replicate the same router. You just need to wire the switches to the right places, that's it. It's used in one of the earlier supercomputers, if you will, multiprocessor machines. It's called the MYU Ultra computer. The reason I'm introducing it because I'm going to talk about something else related to this in a little bit. And you can read this paper that describes it. Again, you can analyze the network for different contention patterns. So the way where these networks, multi-stage networks, differ is really in the contention patterns. How much contention do you have and how much contention you don't have, and also whether the stages are the same or not. So one of the interesting things in this ultra computer was these switches were not just switches, but they were doing some computation while the message was traveling. So you could actually encode some simple operations into the message. For example, if you're fetching a memory location, you could add to it. And all of the switches could do this operation. And this is actually very nice. It's called combining operations in the network. The idea is to combine multiple operations on a shared memory location. So for example, if you want to do some sort of synchronization, test and set, basically you're fetching some value and you're setting that value to true, right? Or you're testing it and then setting it to true. So you could implement it as fetch and OR. You basically fetch it and you OR it. And once you OR it, it becomes true, it becomes 1. And anybody else who gets that message sees that somebody else already ORed it, right? That's the idea. If you want to see more detail, you can take a look at the paper. But basically, this is an Omega network that switches multiple fetch and add operations. Fetch and add is the more general form in NYU Ultra computer. So fetch and add means you fetch M, you return M, and replace M with M plus I. And while the message is traveling through the network, if somebody else requests M, the router figures that out and gives the requester M plus I, and then adds I to the location. So basically, the value of the location changes while the messages are transported within the network. So where could this be useful? When this sort of operation exists when parallel processors modify a shared variable. For example, if you want to obtain the chunk of an array, and if every processor wants to get the next chunk in an array, but you don't care which chunk is assigned to which processor, you basically start with the array index 0. That's a memory location that says this is the array index that I'm going to allocate to this processor. And each processor gets a chunk. Let's say one processor wants 256 elements of the array. It increments that index by 256. And the next processor just needs to know that 256 and needs to increment that index by some amount. That could also be, let's say, 512. And the next processor adds 512 to it. So all the next processor needs to know is the index at that point, 256, adds 512, that becomes 768. And the next processor who receives that, all it needs to know is that it's incremented to 768. This way you can do synchronization across the network without requiring going to the same memory location to figure out what is the value of that location. Right? Because every processor, whenever it fetches that location, the network automatically increments. And if somebody else requests that location while the thing is traveling through a switch, the switch automatically gives the updated value of that location to the processor that's requesting it. It's beautiful. It's a form of in-network computation, very simple form. And this allows the value to be updated in the network while not being coherent with memory. So the value is in memory somewhere, but it's not updated over there. But the value in the network is updated, and the processors see the value that's in the network. Of course, the topology affects the correctness of this, right? Because, for example, if you're updating the value that's in this bank, every processor needs to go through the same routers to go to that bank, right? So while the value is traveling over here, you actually get, yeah. But I'm not going to go through this. There's actually a little bit more complexity to make sure that works, but you should read the paper for more detail. How do you make sure this is correct? Any questions? I wanted to give this idea to you because this is a relatively old idea in the 1980s, but it's a form of in-network computation. And I think it's a very good idea. The paper shows that there's a lot of benefit that they get when processors are actually synchronizing with each other whenever they're trying to get tasks from memory. Okay, so combining essentially reduces synchronization latency. And by how much you can read that paper, but okay, let's see where we are right now. Now let's go a little bit more and then we can at least finish the multi-stage networks. So this is another multi-stage network. It's called Butterfly. Looks like a butterfly. Basically it's equivalent to Omega network. It's indirect as we've discussed. It's used in one of the older machines, BBN Butterfly network. And there are actually interesting issues related to it. I'm not going to go through this in detail, but one of the issues that people found in these networks is you have conflicts, and they cause what's called tree saturation. Essentially, it's congestion that cause some saturation of the tree. You can think of it that way. And as a result of that, you have congestion problem. But you can actually randomize the route selection in this case, because there's a lot of connections in this case, and that helps to get rid of that saturation. So essentially here you can have multiple paths from the same source to the same destination. Let's review these topologies very quickly. I'm not going to go through this in detail. You can study butterflies. So basically we've seen three types of networks so far. I'm not going to include the bus over here. This is Crossbar. This is, well, we haven't seen mesh, but we're going to see mesh in a little bit. And this is the butterfly in this case, but it's an indirect network. And this is mesh, but we've seen mesh in a different way. So you should be able to name the topologies, hopefully. I've already named these. Multistage logarithmic. As you can see, this is indirect, and this is direct. This is direct because endpoints sit inside the network. They're not outside the network only. Blocking, non-blocking, I'll ignore this, but you can take a look at it. So cost is the interesting part over here. So if you look at the cost of this is O(n) squared. The cost of this is n log n. The cost of this is n. So you have basically n links over here, as we will see. That's why mesh is actually very interesting. But we'll see downsides of it also in a little bit. So latency, if you look over here, this is order of 1. You have that link. This is order of log n. Now the downside over here is the latency of this will increase, right? This is square root of n. And as the network grows, this becomes less wieldy. So that's the beauty of where we're going to get to next. So we're going to go to meshes next. But before we go to meshes, I'm going to build up something. Rings. We're going to get back to buses. And how do you actually scale the bus up? Because you can think of meshes as rings of rings also, if you think about it. Okay, any questions? I'm going to take a break for some time before we continue with rings. So you can ask your questions over here right now. Okay, so let's take a break until 1:30, and then we'll continue with rings. Yeah, this is where we left off. Remember, we started with bus, and then we talked about point-to-point, and we were going from point-to-point to more cost-effective topologies. We covered multi-stage logarithmic networks, and mesh is the next step, but I'm going to go back to bus and ask the question, can we make bus a little bit more scalable? Start from the opposite point, as opposed to can we make point-to-point a little bit scalable? And if you want to make the bus a little bit more scalable, the next place you go to would be a ring. A ring looks like this. Essentially, you have processors that are connected neighbor to neighbor. That looks like this. And each neighbor is connected to its own neighbor. And you have point-to-point links between the two neighbors only. Not all processors, but two neighbors. And then the processor is connected, the entire system is connected through what's called this ring, if you will. And if you look at this, well, this is the formal definition, if you will. Each node is connected to exactly two other nodes. Nodes form a continuous pathway such that packets can reach any node. So this is cheap. The cost is ON, links, as you can see over here. And the routers are very simple because you just need to decide where to route. If you want to route from this processor to this processor, you know you should go to the right over here. And this could be a unidirectional ring, meaning you go only to the right, for example, or only to the left. So if it's a unidirectional ring, routing is even easier, right? You basically send a message saying, I want to communicate with processor 5, and then the message gets routed to the right all the time until it reaches processor 5. Are you okay?
Yeah.
Okay.
Just eat.
Okay. So routing is easy, but exactly because of that, you have high latency, right? Because you don't have, you can only communicate with your neighbor to the right if it's a unidirectional ring. As a result, you have to go through n number of nodes if the distance between you and the other node is n. So overall, the latency is ON. It scales with the number of nodes in the system, right? Of course, it depends on who you're communicating with. If you're communicating with this neighbor to your right, then the latency is only 1 hop. If you're communicating with the neighbor to your left, and if you have a unidirectional link, the latency is n-1 hops. Not good. So on average, your latency is n divided by 2, right? Basically order of n. It scales with the number of nodes. Not so good. It's very different from, if you go back to this picture, O1, O log n, and O square root of n. So ring latency is higher than any of these. And it's also, okay, of course you can reduce the latency by making a bidirectional ring, meaning you can send messages to the right as well as to the left. Once you do that, you reduce the latency a little bit more, but it's still ON. You just cut it in half, right? When you're communicating to your left neighbor, it's 1 hop. So it becomes easier to reach. So this, of course, this is not easy to scale. One of the reasons is your bandwidth remains constant. So this is where bisection bandwidth becomes interesting, because as you keep adding processors to this network, your bandwidth, the bisection bandwidth is constant. Your neighbor-to-neighbor bandwidth remains also constant. You're just adding more processors. It's scalable in the sense that you could keep adding more processors. Your links become not so far away from each other, except for this one, but that's okay. This is, you could actually form things in a circle over here, right? Although how do you lay out becomes a problem. Essentially, this doesn't scale really well. But this is used because of its simplicity. Of course, before actually we go through this, maybe we can talk about the contention issues over here. So if you're communicating between this node and this node, and this node and this node is also communicating, you could send messages concurrently. But you may need to do arbitration, of course, depending on how much contention you have on the links. So it's actually not bad in terms of contention, except things can get contended. So this is used, because of its simplicity, it's used in many commercial systems today. The multi-cores very quickly adopted this ring-based systems, and they're becoming more sophisticated. Larrabee is a very good example of a bufferless ring, for example. They actually got rid of the buffers in the ring, and we will see that in a little bit. So this is unidirectional ring. If you look at this a little bit more detailed, if you look at a node, it needs to connect to the ring somehow. How do you connect to the ring? You need to be able to inject into the ring, and you need to be able to eject from the ring, meaning that get a message from the ring. So essentially you have a 2x2 switch, which is very similar to the 2x2 switches that we looked at earlier, to be able to communicate. But this is a very simple switch. And you could have, again, the same choices. You could have buffers, no buffers. You could have circuit switching. You could have packet switching, although circuit switching in a ring may not be that great. Anyway, so the topology is very simple, and implementation is also very simple. You get reasonable performance if n is moderately low, and the performance needs are actually moderately low also. And cost we've already discussed. It's ON cost, n divided by 2 average hop. Latency depends on the communication patterns that you have. So you could, as I said, you could make it bidirectional. You could have multi-directional pathways or multiple rings. This reduces latency and improves scalability. But now you have a slightly more complex injection policy. You need to select which ring to inject a packet into. So this is a single directional ring. You could think of a multi-directional, bidirectional ring as another ring over here, but going the opposite direction, right? It's essentially two rings. Where they interact with each other is when you're injecting or ejecting, basically. Okay, so hopefully that's simple. So now you improve the scalability a little bit. So if you want to improve scalability, you can build hierarchy to the topology. So hierarchy is a very general concept. It's not specific to rings. You could actually have hierarchical meshes, for example. You could actually have hierarchical crossbars if you want. But you could have hierarchical rings also. These are essentially rings of rings. This is one example over here. If you want to build a 16-node system, nodes are, endpoints are the red ones over here. And if you don't want to have a ring that contains all of them, because if you want to have a single ring, that's not very scalable because your latency increases, right? You could build something like this. It's actually much more scalable. You could actually have rings that house 4 of the nodes, and then you could have a ring, that's called a global ring, that connects those 4 rings. So essentially you have local rings, and you have a global ring connecting them. You basically added some additional routers. They could also be endpoints. That's okay, we don't need to go through that detail. But essentially, now if you think about it, your latency is actually lower than a ring that has 16 nodes. Here you have 4 nodes, here you have 4 nodes. And if you want to communicate from here to here, you basically send the message on one side of the ring. It gets to this bridge router, and then it basically goes through the bridge routers. Let's say we're going to sending from here to here, let's say. It goes through the bridge router this way, and then it hops off into this local ring, and then it rings around to the destination. That's the idea. And this could be simple because each ring is relatively simple, and the routers are simple. It's actually beautiful, I think. And you can actually look at this one. This is another way of connecting these 4 local rings, each housing 4 cores. This global ring has higher bandwidth potentially right now, right? And more connections. And this is another way. Now you have actually 2 of these global rings. So depending on the contention and communication patterns, you could use this ring or this ring. Now you have to decide which ring to inject into, right? So it's beautiful. And these are also easy to route. So one of the issues with a 16 ring, if you have lots of processors on the ring, let's say 16 may be too small. If you have 64 processors on the ring, how do you actually lay it out on chip becomes a problem, while keeping the distances the same across all of the processors. Whereas if you have something like this, the layout is actually a lot easier on the chip because you're really localizing the communications, as you see over here. Okay, this is another example. This is 8x8, 64. And this is one example of 64. You can see it's built by these 4 rings, 4 node rings, that are connected to each other in clusters of 16. And then you have another big ring, maybe with higher bandwidth, connecting all the 4 16 clusters. And as you go up the hierarchy, your bandwidth may actually become higher. We'll see that essentially your network becomes fatter as you go into go up in the hierarchy. If you want to go from here to here, you may need more communication bandwidth, assuming communication is actually uniform across all of these. So you can see now that this is actually more scalable if you add hierarchy into a network. You could be lower latency also. This is one example of lower latency. Of course, complexity now increases, right? Because you don't have a single ring, you have multiple rings. But again, that may not be that bad. It's really a trade-off here. And again, as I said, there's nothing special about rings. This could be a bus over here. You could actually have a 4 processor bus over here that's connected via rings. So you still have a hierarchy. And then actually, this could be part of another hierarchy, and then you could connect this thing as a mesh to many of these other things. Right? So you could actually mix these different topologies once you have hierarchy in the topology. You could actually essentially have a heterogeneous topology. Right? Okay, so this is fun, I think, but I don't want to have a lot more fun with the rings. If you're really interested, you can take a look at some of the papers that analyze these issues. So this actually, this particular paper discussed the design and implementation of a mostly bufferless hierarchical ring. What do you do actually if you want to get rid of the buffering that you may need to have in these routers? Because one of the beautiful things is actually you don't need to have buffering over here. If you don't have buffering and if somehow this link is utilized at that point, you basically deflect and send the message routed around a little bit more. And then once the message comes back, hopefully it goes into the ring. We'll talk about deflection a little bit. Okay. So let's talk about, so rings are good. You can scale them up. But maybe they're not as great, especially if you want to have very high scalability. Although I think the jury is still out as to how to construct the topology. So a little bit, so one of the issues with rings is definitely they don't have path diversity as much. So the path diversity is very low. If you want to go from node X to node Y, you essentially have, well, in this case, you essentially have one or at most two paths if you have bidirectional rings, right? You can increase the number of rings to have more paths, but it looks the same essentially. If you add hierarchy, of course, hierarchy changes things a little bit. You have more path diversity. But if you don't add hierarchy, if you want to have path diversity, now the next thing you go into is a mesh. So if you look at a mesh, it looks like this. We've seen it before. Each node is connected to 4 neighbors, north, east, south, west. And you have O(n) cost again. And the average latency in this case is square root of n. So we reduce the average latency compared to a link, compared to a ring. The ring's average latency is O(n). One of the other good things about this is this is easy to lay out on chip, right? You have regular and equal length links over here. So it looks two-dimensional and it works nicely with a two-dimensional chip. And as I said, there are many ways to get from one node to another. You have this huge path diversity now that you've enabled because your routers are more complex actually. So the downside is your routers are complex. But now you can go from this node to this node in many ways, right? You could actually enumerate the number of ways if you're interested. But there are many ways to get from a source node to a destination node. So this is also used, because of its regularity and simplicity, it's also used in many on-chip network prototypes. Not necessarily the, at least early real designs, but it's used in some real designs. But routers are more complex. So now your router is not 2 by 2. In the ring it was 2 by 2. Here it's 5 by 5, right? Because you have 4 neighbors plus the injection and ejection into the node that is connected to the router. So your switch is much more complicated. Okay, we're going to get back to router design, get to router design a little bit. Okay, so mesh is very interesting, clearly. And if you have a packet switch network, this is beautiful. But you could also use circuit switching on top of that. I'm not going to go into the detail. But one of the issues with mesh is it's very, the drop-off on the corners is pretty bad. So if you're a poor thread that's mapped to the corner, essentially you're crippled. Why are you crippled? Because you have only 2 connections over here, right? Whereas if you're in the middle, you have 4 connections. You can basically communicate on all dimensions. Whereas if you're on the corner, you can communicate only with essentially the south and the east here, right? Essentially, this is not a symmetric network. It's not symmetric on the edges. As a result, your performance is very sensitive to the placement of task, whether you place the task on the edge or in the middle. If you're in the middle, you can communicate a lot. If you're on the edge, and if your communication requirements are very high, too bad. Your bandwidth is very low. And you cannot exploit path diversity as well. So Torus avoids this problem. Torus essentially is a mesh that adds links like this. Basically, you connect the edge routers to each other like rings. So the beauty of Torus is you can look at it like this. This is a ring over here, right? This is a ring over here. 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 Basically, you have rings of rings, essentially, on all dimensions. And it's symmetric as a result. Of course, it's not routed as a ring because it's not really rings of rings. It's really a mesh that's symmetric. So you get very high path diversity and also high bisection bandwidth, but you can compute that on your own, that mesh. But of course now it's higher cost. It's harder to lay out on chip. It's unequal link lengths, right? So basically, how do you actually do the link lengths over here? This link looks much longer, right? Well, people are clever actually. You can you can actually view the nodes to make internode latencies approximately constant like this. So this is an example of a ring actually. And ring is viewed this way. And as a result, you get almost equal link lengths if you want to lay this out. You can think about this a little bit. It's fun. So there are actually people who are doing layouts for their lives, and they can come up with fun things. But this is a simple one, of course. OK, any questions? Now, actually, I've opened the can of worms without telling you the can of worms. I call this a ring of rings, but it's really not a ring of rings because routers are extremely complex. So if you want to actually make this torus simpler, you can actually think about it rings of rings, and you can actually make the routers even simpler. So as opposed to 5x5 routers, you may actually get away with 2x2 routers. But now you need to actually somehow communicate between these different rings. So think about that a little bit. That's the beauty of topology. I think simpler topology, simpler routers are always more attractive to build, especially if you're power limited. And 5x5 routers in general are not that great in terms of power, as we will see also later on. So this is very nice. It has very nice properties, as you can see, the path diversity. But building it in a different way, by thinking differently, might be better. OK, so torus. So now let's explore a little bit more topology. I'm going to be less structured right now. Basically, we've come from bus, ring, mesh, torus. And on the other side, we've examined point-to-point, and then multistage logarithmic. Now you have multistage logarithmic and mesh and torus. You can think about the trade-offs between them. But people have designed other types of networks that do not fully obey this regularity or this continuum, if you will. And one of them is trees. Trees look like this. Basically, it's a planar hierarchical topology. And this is one example over here. You essentially have some nodes that are connected as branches. And you have a root node, usually. This one has 2 root nodes over here. In this case, there is 1 root node. And then you have branches. It's essentially a tree. It's very similar to the data structure tree, right? You could actually map a tree data structure on top of a tree and then handle things nicely. So it's actually inspired by, some of it is inspired by that. So it's good for local traffic. H-tree actually is an example that's used throughout the clock signal on a chip. Because clock signal is another signal that needs to be communicated across the chip. And an interconnect is used for communicating it. Essentially, that's no different from any other message, if you think about it, that you want to send from one location to another location. And usually you have some sort of clock tree. H-tree is one example. People are using more sophisticated trees right now. But essentially, if you want to go out the clock signal, you actually go through this sort of tree. This is another example. This is a fat tree. I've already given you the concept. What does fat tree mean? Well, actually, let's first examine the tree. The cost is cheap. It's ON again. Compared to a crossbar. Think about the crossbar as ON square. It's easy to lay out, but it's very regular. The downside over here is if you want to communicate in a tree, communication between these nodes, local communication is not a problem. But if you want to do communication across the higher levels of the tree, root can become a bottleneck. Or as you go up, actually, the upper nodes can become a bottleneck. For example, if you're communicating from here to here, and if all nodes here are communicating with all nodes that are here, essentially, the roots become a bottleneck. The root becomes a bottleneck. You can think of it over here also. So as a result, people have proposed what's called fat trees. This was first introduced in Connection Machine 5. It looks like this. Basically, as you go higher in the hierarchy, as you get closer to the root, the connections becomes fatter. Fatter meaning higher bandwidth. Because you don't need as much communication bandwidth over here, assuming uniform traffic again. You don't need as much communication bandwidth over here because you're communicating between only 3 nodes. But as you go over here, this link needs to carry traffic from many, many nodes. As a result, it becomes fatter. And we've already discussed this principle, right, in the hierarchical rings. This is also a hierarchical topology, except everything looks like a tree if you go inside. In hierarchical rings also, you could actually make the higher level rings fatter. Okay, so let's go into CM5 fat tree a little bit. This is interesting, and you can read about that in this paper. CM5 is a very interesting machine that was essentially built to be a parallel processor supercomputer. It had this sort of fat tree. Essentially, it had 4x2 switches that looks like this. So 4x2 meaning you have 4 inputs and 2 outputs, as you can see. And it wasn't a perfect tree, but it is a tree topology still, because you're going up. And if you want to communicate from here to here, you need to go to this branch. And these are some of the root nodes, as you can see over here. So as you go up, which router you go to was determined in a randomized manner to minimize the congestion and to maximize the balance, load balance across the different links. Because you have some choices, right? Do you go through this router or do you go through this router? And then going down, you go through this router or this router, although going down is a little bit harder to route because you don't have 2 links going to the same router over here. So going up, you actually have randomized routing. And also it had other operations like combining that we've discussed. It also had multicast support. So the network itself actually was able to replicate messages if you want to communicate with multiple nodes, if you want to send message to multiple nodes. You actually are able to replicate the messages as opposed to sending multiple messages from the get-go. So if this node wants to send a message to, let's say, I don't know, this node, and this node, as opposed to sending 3 messages, you can send 1 message, and then the message can get replicated in a higher level node. That reduces congestion clearly. And it also had reduction operators to do addition. So it's actually beautiful. So if you actually look over here, some computation patterns fit nicely to this tree. So if you're adding a lot of numbers, you could map this nicely into a tree and make this computation really parallel. So you can think of 2 numbers being added here, 2 numbers being added here, and the sums go up and they get added here. And every leaf node adds 2 numbers and the sums propagate up. They get added in the intermediate leaf nodes. Well, they're not leaf nodes, intermediate nodes. And then the 2 sums propagate over here and they get added in the root node over here. Essentially, sum is really a reduction operation. As you go up the tree, you're reducing the input that you have. And trees are a very good fit for that sort of reduction operations if you're doing a parallel sum. So that's beautiful. And this particular machine had some support for those reduction operators inside the tree. And to figure out what that support is, you can read this beautiful report. So this is another example. Actually, if your network can be very efficient in some particular computation or communication patterns. If you think about the sum, it fits nicely into a tree. Actually, a lot of the adders could be built based on trees or multipliers based on trees, right? Multiplication is another example over here. Okay. So let's get a little bit more complicated and then we're going to finish the topology part. So people have actually built topologies that look like this. This is hypercube. It's very interesting, I think. It's an n-dimensional cube, or it's called an n-cube. Essentially, this is cube and this is a 4-dimensional cube. And the latency that you have over here is log n, which is beautiful. Radix is O log n, and the number of links is O n log n. You can study this yourself. So the big upside of this is you have low latency because you have a lot of connections over here. The downside is it's hard to lay out in 2-dimensional and 3-dimensional. This is one example of the fancy topologies, as I like to call them. How do you lay this out in 2-dimensional and 3-dimensional? So this was first proposed and implemented in what's called the cosmic cube. If we had more bandwidth to read papers, then I would assign this paper also, because it's a very beautiful paper that talks about message passing supercomputers and how to actually program them and also how to design them. And this is the example that they had with the cosmic cube. It's essentially a 6-cube over here. They call it a binary 6-cube. It's a 64-node machine. And this is a 2-dimensional projection of this 6-dimensional hypercube. As you can see, it's a mess. So it's hard to lay out. But your connectivity is very nice. As a result, you get this nice O log n latency. Right?
So it's very similar to multi-stage networks, but it's not a multi-stage network. Every node, every endpoint is also a node over here, right? So you get the benefit of a multi-stage network in this case, without the cost of a multi-stage network. So if you think about the multi-stage network, yeah, our cost was also n log n. So okay, yeah, with the same cost actually. Okay, we can think about it a little bit more. So there are more topologies, and we could, if you want to talk about topologies, that could be a whole few lectures by itself, but we don't have time for that. Any questions? I'm going to stop the topology over here and move to other important aspects. But hopefully it's clear to you that topology affects everything, right? We talked about routing a little bit. We talked about the switch complexity. We talked about latency. We talked about cost. Topology is a big starting point. And whenever you design a network, you should think about topology first. Okay, so let's move on to the next big thing in interconnects, and that's routing. And routing actually is also a huge lecture by itself. But I'm going to try to make it simple. So when you talk about routing, you first need to have a mechanism. So a mechanism means how do you actually do the routing? There's some mechanism, and also this is very tightly coupled with your topology as well, right? For example, if you have a regular topology, your routing can be a simple arithmetic function of your source and destination and your current location of where the packet is. Essentially, the router needs to determine the route. How does it determine the route? Where to send the packet to. If you have an input port and output port, routing is mapping the packet from the input port to the output port, and the generalized routing problem is doing that for all of the routers between the source and the destination. If you have a regular network, you could do it with simple arithmetic operations. If you think about a mesh, for example, if you want to go from this source node to this source node, you know the XY coordinates. And essentially, you could calculate based on the XY coordinates whether you should go to the right or to the left, up or down. Right? That's very simple. This is called dimension order routing. Basically, dimension order routing means you go through the X dimension first and then the Y dimension next to get from source to destination. Let me actually see. We're going to look into this a little bit more, but I think I will need this figure in a little bit anyway. I don't know if people can see it, but so let's draw this simple mesh over here, 4 by 4. Can you see it? Is it good? No? How do we actually do this? Let's see, light. Projection? No. Conference? How did we do it? Room? Do you remember? Blackboard? Lecture? None of that changes. Do you remember? Yeah, I want to basically turn that off somehow.
Turn it down, turn it off. Close.
Oh, okay, there you go. That's better, right? Isn't it? I think so. Okay. Basically, you have these connections. And routing here is simple. Essentially, let's say you want to go from here to here. You have many, many potential routes, of course. But one way of routing this message from here to here is interesting. You go through the X dimension first, to the right, and then Y dimension. And that's easy to figure out. In this router, you look at the coordinates of this, 0, 0. The coordinate of this is 0, 1, and 0, 2, 0, 3. And you basically know the destination. What is the destination? What did I do wrong? 1, 2, 3. Oh, okay, 3, 3. This is 3, 3. So basically, you compare the source and destination and go through the X dimension first, such that you increase the Y. And then once the Y becomes equal to the Y of the destination, you start increasing the X. Right. That's the idea over here. It's very simple. So the routing route computation is very simple in this case. But of course, one downside of this sort of routing is you don't exploit the path diversity. If you always use XY routing, this is called XY routing or dimension order routing, XY routing, you have a lot of path diversity here. You're not exploiting it, you're always going through this route. If everybody is going through that route, you have a lot of congestion in the network, right? So we will see that this routing algorithm is not good for congestion because there's a lot of links over here that are not used if all of the nodes are communicating through XY routing and the communication is happening between these nodes to this destination node, right? So there's a trade-off between simplicity and congestion that you have over here. So let's go back to open. I guess, I don't know which one's better, but hopefully you will tell me if you cannot see it. So that's arithmetic based. You could also have source based routing. You could have the source, actually I'll put this up. You could have the source specify the output port for each switch in the route. Basically at this source, you basically determine everything. Of course this is much harder to do, clearly, but it will have advantages. Because in this case you have simple switches, right? There is no control state. The switch basically just looks at where should it send the message. It doesn't need to determine where should it send the message. It just looks at the header because somebody else already determined that. So source-based routing is also interesting. But you have a large header in this case because source tells, okay, in this switch it needs to go this way, in this switch it needs to go this way, in this switch it needs to go this way, in this switch it needs to go this way. It needs to encode all of that information into the header of the message that it's sending. So it's a large header, but the switch is very simple in that case, right? So the switch doesn't need to do a lot to determine the route. And if you want to do a table, so you can also do a table lookup based. Basically, you can index into a table for the output port. In this case, you have a small header. So in this case, switch has a table inside it. And the table says if you want to go from this input port to this output port, basically, if you're coming from this input output port and if you want to go to this destination, you need to take this output port. That's the idea. You have the source input port and then the destination that you need to reach. You use them to index into a table, and the table tells you the output port, right? And this table can be dynamically updated depending on the congestion in the network. So that's more flexible than arithmetic routing, as you can see. Arithmetic routing can be less flexible. But your complex switches may become more complex if it's table lookup based because now this table needs to be configured somehow. And if you want to actually change the configuration of the table, that becomes even more complex. So a lot of the existing internet switches are table lookup based. Basically, you need to have some sort of table that's called a routing table that changes dynamically. Okay, so that's routing mechanism. And we could talk more about that. Clearly, it has a lot of effect on how you actually do the routing. There's also a routing algorithm, which also has a lot of effect in terms of many things. And there are three types of routing algorithms that we're going to cover. One is deterministic. Deterministic means given the same source-destination pair, you always choose the same path. It's deterministic. Your path is deterministic based on the source-destination pair. Oblivious is your path is independent. Basically, you choose different paths without considering network state. Essentially, your path is independent of the source-destination pair, if you will. There's another way of putting it. You go from source S to destination D, and you may always choose a different path, independently of the network state. And there's also adaptive. You can choose different paths when you're going from source to destination, but you adapt to the state of the network. You're not oblivious to the state of the network. And there are many algorithms that fall into these different categories. So if you're adaptive, then the question is how to adapt, right? If you're oblivious, there's also the question is how do you become oblivious? We'll talk about that. How do you adapt? You can take into account local and global feedback. So basically, if you want to go from here to here, for example, you may actually know that this part of the network is congested. So that's a form of global feedback. And you try to avoid it. So you send the message down this way. Clearly, that's not a deterministic algorithm. That's an adaptive algorithm. Because somebody somehow tells you that this part of the network is not good to route through. So you go through this way. Right. which means that there needs to be some mechanism to get this global feedback. Local feedback means if you want to go from here to here, you just look at the immediate links. Which one is congested or not congested? Downstream routers over here. And if this says I'm congested, then you route down. If this says I'm congested, you route this way. You take the X or Y first, depending on who is congested locally. Of course, local feedback may not be good enough because you route down and then you found out that actually there's a lot of congestion over here, right? So local feedback is not necessarily good. Global feedback is not easy to gather and also not easy to adapt because global feedback might change over time and your global information may not be correct after some point in time, right? So there's a lot of trade-offs over here which we're not going to get into. How to adapt also has another issue. Are you adaptive minimally or non-minimally? Minimal path means the minimum number of hops to go from one source to a destination, a source to a destination. So if you look, if you want to communicate between this router over here, this source over here and this source, there are two minimal paths, right? You can go this way. Actually, there could be more than two minimal paths. There are actually many minimal paths. You could go this way, you could go this way, you could go this way, and they're all minimal paths. Minimal paths meaning the minimum number of hops to take. But you could also have non-minimal paths, meaning you could do this, right? You could do this zigzagging, and then eventually reach your destination. You could be minimally adaptive or non-minimally adaptive, and you could still adapt. But if you're non-minimally adaptive, you may actually be taking a longer path than you actually really need, but you may be avoiding congestion in the network. So we're going to talk about non-minimally adaptive routing also. In general, non-minimal adaptive routing is the most flexible form of routing, but it does have issues because how do you guarantee forward progress if you're non-minimal, right? If your routing algorithm is always minimal, you always guarantee forward progress, right? Unless you have deadlocks in the network. Okay, so let's go into a little bit more detail in these. Deterministic routing, all packets between the same source destination pair take the same path. This is also called dimension order routing in meshes. It's also called dimension order routing. And I've already given you the idea. First, traverse the dimension X, and then traverse dimension Y. This is called XY routing. You could also do the opposite. You first traverse dimension Y and then dimension X. That's called YX routing. So this is actually used in early Cray machines, not early, Cray T3D machines and many on-chip networks because it's very simple, right? And it makes the router also very simple. Well, I already said that. And it gives you deadlock freedom. We're going to talk about deadlock in a little bit because if you don't do the routing well, you can actually run into deadlocks in the network, especially when you have buffers. This is deadlock free because there are no cycles in resource allocation. There's no case that you run into where you're waiting for a resource and the resource is hogged by someone else and that someone else is waiting for a resource that's hogged by someone else and there's a circle in the cycle in that resource allocation because everybody goes through XY, 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 XY. So there's no case where you can actually run into this cycle in this case, as we will see in a little bit. That's the beauty of this sort of routing. If you want to do more fancy routing, then you may run into these cases where you have cycles and you don't have enough resources, so there's deadlock. Basically, you have to break the deadlock somehow. So the downside of deterministic routing is it could lead to high contention, as we've discussed, right? Basically, everybody along this route takes exactly the same route, even though there's so much path diversity in the network, in case of a mesh over here. Essentially, it doesn't exploit path diversity. These are related. It could lead to high contention because it doesn't exploit path diversity. Okay, so let's take a look at deadlock. This is essentially deadlock means no forward progress. There are many instances of it. I'm sure you've seen deadlock in parallel programming. It's no different here, actually. You basically have a circular dependency on the resources. In this, I like this example because this shows that each packet waits for a buffer occupied by another packet downstream. So if you look over here, this packet is waiting for this buffer to become free, and packet 4 is holding that buffer. Packet 4 is waiting for this buffer to become free. Packet 1 is holding that buffer. Packet 1 is waiting for this buffer to become free. Packet 2 is in that buffer, and packet 2 is waiting for this buffer to become free, which is held by packet 3. So essentially, you have a circular dependency in resource allocation, and you don't have a free resource, and you cannot make forward progress. Not good. This is actually determined first and foremost by your routing algorithm. Of course, it's a function of your topology also. If you had many links, for example, you could solve this problem. So how do you handle deadlock? One way of handling is ensuring your routing algorithm is deadlock-free. Avoid cycles in routing. And dimension order routing is deadlock-free. Essentially, you cannot build a circular dependency or any circular dependency that leads to deadlock. And you can think about that. Why? Because you're really restricting the turns each packet can take. This packet can only turn to the right and then down. And every packet can only turn to the right and down. There's no packet that can turn the opposite way. As a result, you cannot build this circular dependency in the resources. It's beautiful. Of course, it comes with a downside. The efficiency goes down. Or, I mean, there are multiple solutions actually for deadlock. The other solution is avoiding deadlock by adding more buffering, escape paths, meaning that you over-provision your buffers such that deadlock will never occur. You need to be careful with this, of course, because how do you over-provision your buffers? You need to know how much injection will happen into the network such that you always have enough resources, regardless of the worst case. That over-provisioning is extremely expensive. Actually, we will talk about getting rid of buffers in the network as much as possible. So this solution is actually not so easy, but it's also employed. These are called escape paths. Well, that's one way, over-provisioning. Or you could have escape paths. Basically, you could have multiple different buffers that you could send things into. If you actually have the circular, maybe you don't know if you have the circular dependence, but you sometimes send requests to some other buffer. That's called an escape path in a different channel, as we will discuss in a little bit. Or you can detect and break deadlock. This is a bit harder to do. Basically, you figure out that you're not making forward progress, and you figure out that that's because of a circular dependency, and you preempt the buffers. You could basically, there should be a state machine that's monitoring things and seeing that there is no forward progress, and it could basically say, okay, I have a deadlock here, so I'm going to drop this packet such that everything moves. Now this is more complicated, right? Because now you need to actually have an engine that looks at whether deadlock is happening in the network. So usually if you can avoid cycles in routing, that's great. If your routing algorithm is clean, such that it doesn't lead to deadlock at all, and you can prove that, that's great. These other solutions are usually hairy. So this is actually a beautiful paper that talks about the deadlock issues. It was in ISCA 1992. The idea that's proposed in the paper is how to design a routing algorithm in a principled way to avoid deadlock in a network. And the idea is very simple. You analyze directions in which packets can turn in the network. You determine the cycles that such turns can form and prohibit just enough turns to break the possible cycles. And you can see this, basically the 4 turns allowed by the XY routing algorithm here. These are the turns that are allowed. As a result, you cannot form a deadlock. Anyway, I'm not going to go through this in detail, but this paper shows that you could actually have other algorithms that are more deadlock-free and that are more efficient, but they become more complicated. Okay, so that's deterministic routing. Let's talk about oblivious routing. Oblivious routing is not necessarily deadlock-free, but I wanted to talk about deadlock over here, because deadlock happens whenever you have resources. It doesn't matter. It's not really dependent on how you do the routing. Oblivious routing, non-minimal routing, adaptive routing, all of them are prone to deadlock, so you need to handle them. You need to ensure that you don't have this circular dependency on the resources. But remember, we were talking about deterministic routing. Deterministic routing is one way to avoid deadlock, but not all deterministic routing algorithms are deadlock-free. If they have too many turns that are allowed, they're not deadlock-free. Okay, so oblivious routing. This is the second general routing algorithm type. And this is one example of oblivious routing. This was developed by Leslie Valiant, who was also responsible for the box synchronous parallel programming model, execution model. He won the Turing Award for all of that. And the idea is very simple, basically. The goal is to balance the network load. You don't have any other goal in life. You want to utilize your links really well. Balance the load across the network. And if this is your goal, you basically randomly choose an intermediate destination to route the packet to, and then route from there to the destination. Between source and intermediate destination to the destination, you can use some other type of routing. Or you could use another oblivious routing as well. Right? That's the idea. So basically, let's take a look at an example over here. If you want to do oblivious routing over here, this is your source, this is your destination. And if your goal is to balance the network load, you don't do XY routing. You basically randomly pick a node, intermediate node. Let's say we pick this one. And then we do XY routing over here to get to that node. And then from this node, we do XY routing over here. The next time we want to route from here to here, we randomly pick another one. Let's say the next time the random node is this one. We do XY routing over here, and then XY routing over here. And if you have a lot of communication, eventually you utilize all of your links and you balance the load. And somebody else communicating from different nodes actually do the same thing. As a result, your network utilization becomes randomized nicely. This is great for load balance, basically, in the network. Essentially, if you want to utilize all of your links equally, if you're truly random in your choice of the intermediate node, you will do that. Of course, this is now non-minimal. Packet latency can increase, potentially, depending on how you do the choice of the randomness and how you do the intermediate routing. But there are optimizations also. So actually, there could be optimizations on this. You may only do this on high load, such that you don't increase the latency. Or you can restrict which intermediate node to choose. You can restrict the intermediate node to be close. Right? So packet latency increases because your random choice may actually take you somewhere else, right? In this case, actually, it doesn't increase because these are the farthest possible source and destination pair. But if your source is this one, and your destination is this one, let's say, if you're strictly obeying oblivious routing, you may actually route this packet to here first, and then from there to here, right? Of course, it sounds not so intelligent, but that's the pure form of oblivious routing. But you may want to optimize this. You may say, oh, okay, if I'm the nearest neighbor, maybe you don't do that. That's good. Or maybe you do this only when you have high load in the system. Or maybe you restrict the intermediate node to be close. You don't basically go from here to here and then back to here. You basically divide the network into some quadrants or vicinities of the destination, and you try to route first closer to the destination. It's still more oblivious, but it's more intelligent oblivious, if you will. Okay, so the key takeaway is this is good for randomizing and balancing the network load such that your links become utilized well, but link utilization doesn't go well with the latency necessarily. Okay, so adaptive routing essentially adapts to the network state. Oblivious routing doesn't adapt to the network state. You randomly choose this regardless of the network state, right? You don't know anything about the network state. You could use the idea of randomization to do adaptive routing also. Adaptive routing essentially says you look at the network state when you determine how to route, what is the next router you should go to. Minimal adaptive means you always choose a productive output port. Productive output port is the port that gets the packet closer to its destination. You don't choose a non-productive output port. Non-productive output port is an output port that gets the packet farther away from the destination. Right? And that's the difference between minimal and non-minimal. And in minimal adaptive, you use the network state to pick which productive output port to send the packet to. And network state could be multiple things, as we've discussed. It could be the downstream buffer occupancy. It could be more global knowledge from the network, which I'm not going to get into, but you can think of many examples. So the upside of minimal adaptive is it's aware of local congestion. But if you're minimal, it restricts available link utilization, meaning load balance. So this is not as good as oblivious in that case. Oblivious actually, well, it depends actually. Oblivious doesn't adapt to the network state, right? So people are therefore develop non-minimal algorithms also. Non-minimal is also called fully adaptive, meaning that you can route the packet to anywhere. It could be a non-productive output port. This is also called misrouting. You basically misroute the packet. It essentially means you take it to a non-productive output port. You can achieve better network utilization and load balance if you're non-minimal adaptive. But now you have a problem, which is you need to guarantee live lock freedom. What does live lock mean? Basically, you can have a packet that never gets delivered to its destination, right? Even though it's in the network. Because you're always routing it far away from the destination, right? Or the packet is circling around. So you need to solve this problem, in addition to the deadlock freedom. Okay. So adaptive routing is actually interesting because adaptive routing is actually somewhat necessary in general, especially if you have a lot of faults in the network. If some links can go down, you can avoid faulty links and routers. You can route around faults. You could modify the deterministic routing also. So if you have faults actually over here, if this link is not usable, you need to go around it. In some cases, you basically give up and you say the chip is unusable. But if you have some ability in your routing to adapt a little bit, such that when this is detected to be faulty, this one routes down as opposed to this way, then you can actually fix the fault, right? So you can route around faults. So adaptive routing is really necessary for fault handling. Deterministic routing cannot handle faulty components, at least in the strict sense of the term deterministic routing. You need to change the routing table to disable faulty routes. And that's by definition not deterministic in a sense, right? Once you change it, it's deterministic, but you need to have the mechanisms to change it. Which has implications on your router, because your router needs to be able to replace its routing table, right? It cannot be simple arithmetic that you use. So that's the subtlety here. Of course, you need to find, there should be mechanisms to detect the faulty link and router, right? Okay, so there are a bunch of examples of this, and it's actually much more sophisticated. Once you design a network, you want to guarantee delivery, and you want to handle faults, and you want to also have an algorithm that's good in terms of load balance, performance. So it's actually a complicated design space. But this gives you just one example over here. Okay. So this may be a good place to take another break. Any questions? So let's take, I guess, 7-minute break until 34. And then we'll continue with buffering and flow control. I'm going a little bit slower than I expected. Okay. Okay, so let's talk about the last big component of interconnection networks, and last but not the least, it's buffering and flow control. And again, as I said, this is tightly coupled with the routing strategy as well as the topology. Maybe less the topology, but routing and buffering and flow control, they're very much coupled with each other. Topology usually determines what kind of routing algorithm you want to implement. Okay, this is, we already discussed some of this, circuit versus packet switching. Actually, this choice affects a lot of your buffering and flow control decisions. Circuit switching, you set up the path. You don't need any buffers, basically. If you're operating in this mode, that's great. You don't need any flow control because your flow control is handled by setting up the path and isolating it from anything else. Flow control happens only to ensure that somebody else cannot use that path. So there's still some flow control in there, but it's a lot simpler. Packet switching, on the other hand, you may or may not need buffers in this case, and you definitely need some flow control in this case. So circuit switching and packet switching is definitely something that affects your buffering and flow control. I'm going to focus more on packet switching for the rest, but a lot of the things that we discuss is applicable also to circuit switching. So basically, if you want to do some sort of packet switching or communication, you need to have a message format. And I'll call it the packet format. This is boring. Clearly, you need to have some sort of header in the message that encodes your destination, for example, or some routing and control information. If you're doing source-based routing, the entire path. If you're doing circuit switching, which circuit that you're using, etc. So you need to have some sort of header, control information. You need to have the payload. Payload is whatever you want to communicate, basically. That's a cache block or a control message or a coherence message. It carries data. It can be further divided into stuff which I'm not going to go into. And you can have error codes also, like a checksum, so that the receiving routers or intermediate routers can check that this is still correct, right? You could basically have a checksum on the header and the payload, right? Or you could have separate checksums on the header or the payload. And it's generally at the tail of the packet, so it can be generated on the way out, basically. Because you've already received everything, you just need to do the checksum, some sort of error correction calculation, and then check it with the tail of the packet. Okay, so that's the boring part, maybe. I mean, all sort of networks need to have some sort of packet format. The more interesting part is this question. We need to handle contention somehow in a network, especially in a router. And we're going to go into the building of routers in a little bit. We're not going to go too much into it, I think, but basically, if you have two packets that are trying to use the same link at the same time, what do? By the way, feel free to circulate around so that people can have multiple rounds. You can do the routing of the Turkish delight. That's the packet. And then you can run around and lose some weight as well, if you have extra weight. Okay, so then the question is, what do you do? Two packets coming from different input ports are trying to go to the same output port. What are your choices? Well, we've discussed one choice, buffering one, right? You could buffer one of the packets and let the other one use the link in the next cycle. And then in the next cycle, you take the buffered one and send it out. Are there other choices? Any questions? Any thoughts? What else can you do? Yes? You can drop one, right? And then, of course, tell the sender to resend it. So this comes with some complexity. You need to communicate back to the sender saying that you drop one, unless you don't care. But in most cases, you care, actually. So you need to tell the sender, which means that you need to have a communication path, reliable communication path back to the sender. And you cannot drop a lot on that communication path, because otherwise you run into this problem. You keep dropping packets and you never send the packet. What else? Any other choices? Buffer, drop, yes?
I mean, you could also drop but implement reliable transport on top of the unreliable. So have acknowledgements from the destination instead of from the dropping path.
Okay, how would you do that?
Sort of like TCP with acknowledgements that are numbered.
That's true, yes, that's true, basically. Yeah, that's one way of actually handling the dropping, you're right. Yeah, there are multiple ways of handling the dropping. You may not need to notify the sender, but maybe the destination somehow figures out. Yeah. Although the first time you're sending the packet to form that connection, you still need some reliable path to the sender, right? Because the receiver doesn't even know that they're going to receive things. But yeah, that's good. So dropping actually has a lot of complexity, as you can see. Buffering is a lot easier, perhaps, but it's a choice, yes?
One could send the packet on the wrong link.
Exactly. The third one is actually misroute one. We already covered this, actually. It's called deflection also. You don't send it to the link that it needs to really go to, productive link, but you send it back, let's say. It's coming from here. Okay, I don't want it. Get it back, right? Or some other link that's free. So these are three fundamental choices. I don't know if there's any other choice. Any other choice would be a combination of these things, I think. And there are trade-offs associated with this, and we're going to look at these trade-offs. Clearly, buffering requires buffers. Dropping requires some sort of communication to the sender. Misrouting requires something else. Eventually, you need to route it correctly, right? You need to ensure there is no live lock. But if you actually do dropping, you can get rid of buffers. If you actually do misrouting, you can also get rid of buffers. Right? So that's the upside. And you could use this in a combination. If your buffer is full, you can start dropping. Or if your buffer is full, you can start misrouting. Right? So there are very interesting trade-offs over here. We're going to talk about that. But let's talk about some flow control methods. So you can think of this as buffering and flow control merged together. Basically, we're controlling some flow. One sort of flow control method is circuit switching, as we've discussed. You set up the circuit and control the flow into that circuit. Bufferless is another flow control method. We're going to look at store forward, virtual cut-through, and wormhole. Circuit switching revisited. The idea is to pre-allocate the resources across multiple routers for a given flow. When I say router, it's the same as a switch. Basically, you need to send a probe to set up the path for pre-allocation. And resource allocation granularity is high in this case. The allocation granularity is an entire path, and no one else can use that path. But the big upsides are there's no need for buffering, no contention for that particular flow. Flow's performance is completely isolated at that point. Latency is low, as we've discussed, and you can handle arbitrary message sizes. Actually, once you start the circuit between the source and destination, you can send megabytes and megabytes of data, right? You just need to break it into packets or the flow control units. Well, whatever the network can transmit. The downside is you get lower link utilization because two flows cannot use the same link at the same time, and you have the handshake overhead to set up a circuit, as we've discussed. So that's one way. Another way is bufferless deflection routing. We're going to look at this a little bit more. Basically, you don't have any buffers in the router. When the two packets contend for the same link, one is deflected. This is actually a really old idea. This is a seminal paper that introduced this idea among many, many other ideas in distributed communication networks. They also called it hot potato routing. You can think of this as a packet being a hot potato. No one can hold it for too long. You cannot buffer it. You basically send the potato to someone else, to your neighbor. And you don't care who you send it to. Basically, you just want to get rid of the potato because it's too hot. And the idea is very simple. When two packets want to, let's say, go through the same destination in this case, and they arrive at the same router over here, the router doesn't have buffers. The router sends one to the destination, but sends the other one to a non-productive output port. So the blue one is basically taking the scenic route, if you will, here over here. It's taking the longer route, but eventually it's reaching its destination. So we're going to revisit this. It's nice. So new traffic can be injected whenever there's a free output link. So you're actually monitoring the output links because you don't have buffers. You just monitor which links are free or which links are not free and inject based on that. So basically, this is a buffered router. If you have buffers, the buffers actually look like this. We're going to go into a little bit more detail later on. But if you have, basically it's a mesh router. It's a 5x5 router. You have 4 neighbors and the local injection ports and 4 ejection ports, output ports, and the local to that particular endpoint. So it's a 5x5 router. It's relatively complicated. And if you do deflection routing, you get rid of the buffers essentially. You buffer the packets in the links, or links act as buffers if you think about it that way. And pipeline latches. Of course, you have pipelining and you need to have latches to ensure there's pipelining. So the deflection routing logic becomes a little bit simpler. But we will revisit this tomorrow. So there are a bunch of issues in bufferless deflection routing. Because it's non-minimal adaptive, non-minimal because you can send it to a non-productive output port, you have live lock. You actually have router complexity issues, which we will talk about. Because it's not as easy because you need to solve the live lock problem. Live lock is not easy to handle. So buffered networks have the deadlock problem. Bufferless networks have the live lock problem. And they're not as either one is not easy to handle, but you need to handle it. And also there's another issue with bufferless networks, which is performance and congestion at high loads. We will talk about that. And if you're interested, you can read this book chapter that talks about a lot of related issues. Although this is not as up to date as you can see over here. Okay, so let's take a look at other store forward control, flow control methods that are assuming buffering. So we're going to assume buffering right now. We're going to assume packet-based networks. Store and forward is an early method that's developed to do the buffering. Basically, you copy the entire packet into the router before moving to the next node, before you send the packet to the next node. Basically, the flow control unit is the entire packet over here. And you wait for the entire packet to arrive. So let's say this is your source to this destination. If you want to do that, you need to wait for the entire packet before you can route it. This leads to high per packet latency. And it requires buffering for the entire packet in each node. So let's take a look at this. Basically, source has the packet. Because it has the packet, it can now route it to the next router. So you have a routing algorithm. It says, send the packet to the next router.
And basically, you send the packet over 4 cycles because the packet is bigger than the link. It takes 4 cycles to send the packet. And this router cannot route the packet before it receives the entire packet. And then once it receives the entire packet, it can start routing. And this router receives it after 4 more cycles. This router cannot route the packet until it receives the entire packet. And then it goes like this. So it's slow, as you can see. You need to wait for the entire packet. And this is how networks used to be designed at some point in time. But this is not very high performance, as you can see. Although it has the advantage that you know that the entire packet is there before you start routing it. So it may be more reliable. The key question is, can we do better? And the answer is yes. So this is another form of flow control. It's called cut-through flow control. You basically start forwarding as soon as the header is received and resources are allocated. Basically, you have the packet at the source, and there's a huge reduction in latency. You can still allocate buffers and channel bandwidth for full packets. As your cut-through allocates buffers and channel bandwidth for full packets. Let's take a look at it. So it basically sent the header. You break the packet into header, body, and tail. And then now packet is distributed across routers, right? The header can go before the full packet is received. And the body and tail are in different places. So you can see that the header is everywhere. Well, now the packet can be distributed across the network. So this is good because your latency is reduced, header is received very quickly, and the packet is overall received well, the tail is received late, of course, but there's a large reduction in latency. But we still allocate buffers and channel bandwidth for full packets in this case, which means that you're really wasting resources. Even though you don't need so for example, at this point, you don't need allocation of the buffer for the entire packet over here, you still allocate for the entire packet. That's true here, that's true here. So it's wasting a lot of resources. So the key question is, can we do better? And we're going to do better in a little bit. So what to do if the output port is blocked? So the cut-through flow control lets the tail continue when the head is blocked, absorbing the whole message into a single switch. Basically, it requires a large enough buffer to hold the largest packet. Essentially, so if the output port is blocked somewhere over here, actually I don't have that animation over here, sorry. But basically, the entire message needs to be buffered in the router, which requires a buffer large enough to hold the largest packet, and it as a result degenerates to store and forward flow control with high contention. So not good. So the key question is, can we do better? And the better is actually wormhole flow control. In this case, you don't do flow control and resource buffer allocation at the packet granularity, but you do it at a much smaller granularity. And the granularity is really the FLIT granularity. That's the buffer and bandwidth allocation unit. That's why it's called flow control digit. So you can have a header and body FLITs and tail FLIT. And in each router over here, you have resource only for the FLIT that you're buffering. So you have only one FLIT that's buffered. You have one buffer that's allocated for this FLIT, one buffer that's allocated for this FLIT, and one buffer that's allocated for that FLIT. You don't need buffering for the entire packet because you do the buffer allocation at a much smaller granularity. It's a very simple idea. And FLITs are sent across the fabric in a wormhole fashion. That's why it's called wormhole flow control. So if you think about this looks like a worm. The head of the worm is here, the body is distributed across some routers, and the tail is at the very end. So basically, body follows head, tail follows body. It's pipelined. If head is blocked, rest of packet stops. And the interesting thing is routing or source and destination information is only kept in the head. So basically, head leaves some breadcrumbs, if you will, to ensure that body and tail gets routed in the right way. So you need to have some state that's in previous routers for that purpose. So how does body and tail know where to go? Essentially, that's what I said. You need to have a previous state, and that makes it a little bit more complicated. But in this case, latency is almost independent of distance for long messages because you're actually pipelining the entire packet across the network. That's not completely true, of course, but now your header can actually reach the destination very quickly, and body and tail flow. So the big advantage over store and forward flow control is you get lower latency and more efficient buffer utilization. You don't need to allocate buffers for the entire packet. Limitations, of course, this also suffers from limitations, which is called head of line blocking. If head FLIT cannot move due to contention, another worm cannot proceed, even though links may be idle.
And I will give that example to you. This is really a problem with first in, first out queues. You have these input queues, you have these outputs, and you have this router switching fabric. This is input port 1, input port 2, and this is where things should go, output ports. This should go to output port 1, this should go to output port 2, this should go to output port 1. If you look at this, both of the flits that are at the head of these input queues, they both need to go to output port 1, right? So you send that one. In the same cycle, you cannot send this one because if you look at just the head of the queue, they both want to go to 1. If you do the arbitration just by looking at the first thing in the input queues, both of these flits want to go to output port 1. As a result, you send this one, you buffer this one, but you're not aware that there's someone else that wants to go to output port 2 because you were doing arbitration just based on the heads over here. Right? This is called head of line blocking. It's kind of not nice. Actually, if you were looking at all of the possible flits over here and deciding what to route, this wouldn't happen. Right? Basically, if you were looking at in this input queue, you're looking at all of them, and you're picking one, the head to go to output port 1. Here, you do arbitration also. You say, oh, output port 1 is already allocated, so I'm going to look at output port 2. Is there anyone who needs output port 2? If that's the case, then you can actually send it over here. But that arbitration actually becomes more complex. It's really out of order scheduling. It's a little bit more complex actually than out of order scheduling. And people didn't want to build routers that way. So we're going to solve this problem in some other simpler way. And the idea is, well, actually, I'm going to demonstrate this a little bit more. Idea is going to be virtual channels. Basically, a worm can be before another in the router input buffer due to the FIFO nature. That's really the fundamental problem. The second worm cannot be scheduled, even though it may need to access another output port, completely separate output port, right? So let's take a look at it over here. Let's assume that this link is blocked by other packets over here. So this green one cannot move. As a result, this purple one cannot move also. So this blue one is making progress. The buffer is full over here. The blue one cannot proceed, right? And as a result, it's blocked. Even though, it's blocked over here. And then the red one comes in. This channel is idle completely, but the red packet is blocked behind the blue one. Blue one needs to go this way, red one needs to go this way. But the red one cannot make progress over here because the blue one is blocking it in the FIFO queue. So you may think that, oh, this is stupid. Why don't we have an arbiter that's more complex? And yes, that's right. You need to have an arbiter that's more complex, but if you don't want to increase complexity too much. And then the red holds this channel. The channel remains idle until the red one proceeds over there. So one solution to this is called virtual channel flow control. The idea is very simple. You don't have a single FIFO queue to look at, to arbitrate. You basically have multiple FIFO queues for each input port. That's the idea. It looks like this basically. This is your input port. As opposed to having a single FIFO queue, which is vulnerable to this head of line blocking, you have multiple FIFO queues. Or you can think of it as multiplexing multiple channels over one physical channel. You divide up the input buffer into multiple simple buffers. Now you of course have the question, whenever you get a packet or flit, which queue do you put it in? Now you actually, if you want to minimize head of line blocking, you need to be a little bit more intelligent, but I'm not going to go into the details of that. Now we are making the router more complex, right? And that's the paper that introduced the idea. So you can think of it this way. You have 16 flit FIFO buffers. As opposed to having a single FIFO buffer, you have four flit FIFO buffers. And now you can actually, you do the arbitration on the head of each of the queues. So you have actually 4 things to choose. Here you can choose only one thing. Looks like my battery died here. Here you can choose only the head over here. As a result, you're vulnerable to head of line blocking. I cannot find that. Okay, yeah, you can choose only this. Now you can choose only 4 of those. If you actually had complete out-of-order scheduling, you could choose any 16, right? But that's expensive. Right? Okay, so basically virtual channel flow control enables you to have 2 smaller queues. If you're blocked by other packets over here, that's okay. Your buffer can become full. Blue cannot proceed over here. But now there's a queue for the red one. And the red one can proceed. It's not blocked anymore. But now we made the router more complicated. A modern virtual channel-based router looks like this. And we're going to stop in a little bit. But basically, you need to manage these input buffers, the virtual channels. You need to decide where to put an input flow. And then you need to do the arbitration. There's routing logic. Essentially, you need to have a virtual channel allocator. You need to have a switch allocator to figure out which virtual channel should be input into the into the switch, and how should the switch be configured. And of course, you need to do the route computation logic. And there's also another thing. You need to actually handle, there's something that's coming in, credits in. This is credit-based flow control. This basically said, can you actually send something to the downstream router? Does the downstream router has enough buffers to handle things? Because that needs to be communicated somehow, and that's not as easy. And that's true for all routers. All routers need to communicate to the upstream routers whether they have buffer availability. Yes?
Why not have the buffers on the output port?
Say it again? Why not have the buffers?
On the output port? Like you have already the crossbar, in fact, you can already disentangle the different.
Yeah, why not have buffers over here, you're asking, right? You could, actually. Okay. You could have them in either way. You could have both input and output, or just output, or just input. And there are different trade-offs associated with it. You can think about the trade-offs. Actually, just output buffer routers are not as easy, because you need to handle the arbitration before, right? But you could, no question about that. I'm just showing something without the output buffers over here. Okay, let's see how much do I want to cover this. Okay, let's cover this very quickly. So basically, there are other uses of virtual channels. One is deadlock avoidance. You can enforce switching to a different set of virtual channels on some turns, and that way you can break the cyclic dependency of resources. Actually, if you have a virtual channel, you can steer traffic to another virtual channel. You can enforce order on the virtual channels, and you can have escape virtual channels, have at least one virtual channel that uses deadlock-free routing. Everything else uses deadlock, not non-deadlock-free routing. You can ensure each fleet has fair access to that virtual channel. That's another way of handling deadlock, but it's more complicated now, right? You increase the buffering, you increase the virtual channels, and you have multiple routing algorithms in this case. There's also another issue, protocol level deadlock, that can be handled by virtual channels. Protocol level deadlock means essentially you may have different packet classes, requests and replies, and you may have a deadlock because those are preventing each other's delivery. And you can ensure that those different data packets use different virtual channels such that they don't prevent each other. And you can, since we don't have time, I'm not going to go into that much detail. This virtual channels enable prioritization of different traffic classes. Some virtual channels may have higher priority than others. And as a result, you can actually differentiate between different traffic classes. So that's another use of different virtual channels. Okay, so let's review flow control very quickly. Store and forward was like this. You needed to allocate things at the packet granularity, and you need to do the routing at the packet granularity also, which was slow and high buffer overhead. You shrink buffers, reduce latency, you get to cut through and wormhole. I'm going to handle them similarly. And then there are other issues over here, which is head of line blocking. And we solve the head of line blocking by using virtual channels. And I've already animated this. This is head of line blocking. And if you actually use virtual channels, you can get rid of that head of line blocking. But actually, as we went from here to here, we increased the complexity. Even though we improved some of the buffering and reducing latency, we actually made the buffer management more complex. And we didn't even talk about buffer management in terms of communicating buffer availability, but since we don't have time, we're going to start with that tomorrow. Okay, I'll see you tomorrow.